Over the last 2 lectures, we've been looking at register machines. We've taken the idea of basic registers and some primitive operations and looked at how to put them together to compute simple things. That computation being controlled by a sequence of instructions that moves values from one register to another through perhaps some operation that does something to those values. We've then generalized to add in the idea of subroutines, ways of getting out pieces of a computation and generalizing them. And we've added in the idea of stacks. You'll recall the goal of a stack was to have a place into which we could store away temporarily values in registers so that we could reuse some computational machinery, some subroutine, to do a subproblem. Then restore the state of the machine and pick up the rest of that computation. We're now ready to do the idea of building a register machine for any kind of computation. And as we suggested a few times ago, we're going to do this for eval. Our reason for completing this process by building eval out of register machines is very simple. Once we've built eval, we have what we call a universal machine. Eval can then evaluate any other expression. It can simulate any other process by simply providing a description of it to eval. So by building eval out of register machines, we will complete our construction of a simple kind of CPU. We will have connected the underlying hardware, simple set of registers, simple set of procedures, and some mechanisms for sequencing instructions of things through those registers. We'll have completed that connection from that up to an actual evaluator or interpreter that can take in any expression in the language and deduce its meaning and return that value. We know the general form that our evaluator should take for a register machine version of eval. And I say that in 2 ways. One is we certainly know the kinds of pieces that will be there. We need to somehow translate the metacircular evaluator that we did earlier down into register machine operations. But the second piece about knowing that form is that we also know that eval is going to have to walk through a recursive loop. Evaluating an expression is typically going to reduce to applying a procedure to some arguments, which will in turn reduce to evaluating a new expression, often the body of that procedure, with respect to some new environment. And that loop, that unwinding of the abstractions, is going to require that we use the stack to save away state. In the terms of evaluating one expression, we're going to need to hold on to some things while we go off and get the value of a sub-expression. To look at that idea and to remind ourselves of what we saw last time, consider the following little example. Here's a special version of factorial that I've written. It's different from the normal version of factorial because normally we would just apply a procedure to one argument, n, to get n factorial. Here, I'm going to deal with both passing in the value for n and a product. And my little procedure here will display the current value of the product and then, depending on whether it's in the base case or not, either return the product or compute the product counting down by 1 and increasing the product by multiplying by n. Now the reason for using this procedure is that we want to think about what happens as we evaluate this. In particular, 2 questions. What's displayed when we evaluate sfact of 4 and 1? And then secondly, does sfact describe an iterative or a recursive process? Think about it for a second, then click the mouse when you're ready to answer. In terms of what's displayed, we see that sfact basically works from the top down. The first time it's called is going to print out 1 because the initial product is 1. Since n is not equal to 1, it's going to call itself again with the first argument of 3 and increase the product by multiplying by the current value of n, which is 4. So we print out 4, and again we'll do it around multiplying that product by 3, and again go around multiplying that product by 2 until we're done, and we can return the value. So we're working from the top down here. Not a big deal. Of more interest is the kind of process that sfact describes. Does it describe an iterative or a recursive one? And the answer we know is it's iterative. There are no deferred operations in this case. It's different than the normal factorial, where we'd have to hold on to that multiplication while we went off and got the factorial of something smaller. By changing the way we think about this, we've converted it to an iterative process. But the question then is, how do I set up an evaluator, a register machine version of eval, that will take advantage of the fact that there are no deferred operations here in order to be very efficient? We saw a hint of that last time in the previous lecture. Let's look at that again in a little more detail. Now our goal is to build that evaluator, to implement eval in register machines. But to do this, we actually want a very particular kind of evaluator. We want to use that idea from last lecture of doing something that's tail recursive. What does that mean? It says the stack should not grow if the procedure being evaluated is actually iterative. This is not true of most languages. For example, most Java and Pascal systems are not tail recursive. And as a consequence, you cannot use recursive procedures as loops. The reason is that, in fact, it will cause the stack to explode on us. And let's look at that. If we think about sfact, we know that syntactically it's recursive. That is, the definition for sfact refers to itself inside its body. And in fact, in most languages, this would say that using an evaluation based on SFACT would have a recursive growth, in which every time we called it, we would have to do an evaluation of the body, which would cause another call. What would that do to the stack in terms of an evaluator if we didn't use this trick of tail call optimization? Well, think about it abstractly. Ignore the fact we haven't actually built eval yet. Suppose our eval did not have tail call optimization. It was just a standard kind of evaluator. Gee, if we evaluate SFACT of 4 and 1, for example, with respect to a global environment, that reduces to doing an evaluation of an application. But because we want to get that value, we have to push that onto the stack. We're going to have to come back and finish evaluating the application after we get the value of the body of this procedure. And that says we then go off and evaluate the sequence of the body of display of something in an if. And of course we know that once the value associated with that is returned, we're going to hand it back to application. But this itself involves another process. So we'd have to push that onto the stack while we go off and evaluate the if. And you see the idea. We keep pushing an expression onto the stack while we go off and get the value of the next sub-piece. In fact, for this example, just to unwind SFACT by one level, we have to push 5 different things onto the stack. Each one of them is an evaluation that is waiting for a value to come back. But we know what that value is. Once we get the final value for SFACT, we're going to hand it back to each one of these expressions in turn, each one of these operations, and they are simply going to pass that value back through. What's the point? I didn't need to keep track of this particular sequence of operations on the stack. I didn't need to have to hold on to the fact that I'm doing an evaluation of an application while I go off and get the subpart, because in fact I know, if I look ahead at the code, that the answer I'm going to return will be passed straight back. If I don't do that tail call optimization, the stack grows each time around the loop. We put on this sequence, in this case of 5 different pieces onto the stack for each recursive call to SFACT, which is going to cause the stack potentially to explode. If we can use that tail call optimization, we can have processes that are inherently iterative behave that way, not using up any of the stack, having no growth in the stack as a function of the argument call. So that's our goal, is to build an evaluator out of a register machine that has exactly this property. With that idea in mind, let's turn to our goal, which is to build a register machine implementation of eval, to basically build a CPU. We're going to take the ideas we saw earlier in the metacircular evaluator. They're done in a more abstract way. We're going to take those ideas and map them down into manipulation of registers using very simple built-in procedures. So we're going to create, if you like, a coupling between the hardware of registers and the idea of the universal machine doing eval. Now, I need to decide what registers and how many I'm going to have. And I'm going to arbitrarily choose 7. This is not a particularly magic number. I could do it with a different version or different numbers of them, but 7 is going to be convenient. And here are the 7 I'm going to use. I'm going to have a register called exp for expression. It will hold the expression to be evaluated. Similarly, I'm going to have a register called env for environment, which will hold the current environment. I'll have a continue register, as we always have before, that holds the return point. I'll have a 4th register called val, that is going to be the place into which I store the resulting value. And in fact, if we stop here, we see those 4 are very similar to things we did earlier. Well, we didn't have the environment, but we basically had a register that held something to be evaluated, we had a return point, and we had a place to store the value. What else do I need? Unev will be a pointer, or a register rather, that contains a list of unevaluated expressions, things like the operand list or sequences of expressions. We'll also use it as a temporary register in other places where we need something to temporarily store away a value. Those 5 registers will be involved in evaluating an expression with respect to an environment. We'll have 2 more registers, proc, which is going to hold the operator value, and argle, which is going to be a list of arguments. And those registers will be used to store the procedure to be applied to a set of arguments and the actual argument list themselves. And indeed, we expect to see a loop in which we take an expression in exp and an environment in env, and we unwrap this into an application of a procedure that's stored in proc and some arguments in argle. That's exactly the loop we saw in eval. We're just going to now map this down into registers. So our goal now is to take that evaluator we saw before and rewrite it or re-implement it in terms of manipulations of these registers. Before we do, though, let's stress a few things that are going to be useful for keeping track of what we do. First, for clarity, we're going to assume a whole bunch of abstract operations as primitives. All of these are things that just deal with the syntax, like getting out pieces of expressions or creating expressions. They don't have to be, in fact, primitive things. It's just easier to think of them that way. We know that we can always re-implement those things themselves in terms of simpler register things, so the abstraction is just going to let us focus on the idea of evaluation. But what we're doing is assuming that those kinds of syntactical manipulations are available as little pieces of hardware. Second, we're going to assume that the environment manipulation procedures are also primitives for the same reason. Third, note that when we talk about an expression being in a register, this means that a pointer to some tree structure that represents the expression is in that register. Note that this means we're going to need lots of const pairs and primitive procedures to manipulate them. We refer to this large collection of pairs as the heap, and we're going to ignore issues of how cells are allocated from the heap to create tree representations, at least for now. It also means that our registers can be of fixed size yet represent larger expressions. They're simply pointers to the tree structure. And as we saw with eval, all we need are procedures that can manipulate that tree structure to load new pointers into registers, getting, for example, new expressions available. Okay, now let's do this. Let's take our idea of eval and let's look at how to map it down into these 7 registers and primitive operations on those registers. The starting point for our evaluator will be a spot labeled eval dispatch. Gee, that sounds like a convenient label because we know eval should in fact be a dispatch on type. So our entry point into this register machine begins there. We're going to see that we come back many times to eval dispatch because every time we want to get a value of some sub-expression, we come back and redo this. Eval dispatch has a contract, and it's shown here in blue. It says the following. It says it expects 3 inputs. It expects the EXP register to hold the expression to be evaluated. As we said, that may be just a pointer to some tree structure. It expects env to hold a pointer to the environment. We expect that also to probably be some tree structure, and we're going to assume abstract operations to actually manipulate it. And of course, it expects continue to hold a return point. Now, when we first start things up, that continue probably points back to the top-level read eval print loop. But of course, we know as we unwind pieces of this evaluation, that continue register is going to be crucial at telling us where to go when we've got the value of some sub-expression in order to complete the rest of the process. There are our 3 inputs. As output, we're going to put the value of the expression in the val register. And in terms of what gets written, we're going to assume for eval dispatch that everything does except continue. That may not always be true, but since we're going to have a wide range of expressions that can be dealt with, we need to be safe about making that assumption. And finally, what about the stack? We expect it to be unchanged. And we remind you that doesn't mean we won't use the stack. It simply says when we come into a call to eval dispatch, the stack will be in some form. And when we finish at the continue point with an expression value in val, we expect the stack to be back into exactly that same form. So what does the register machine code for eval dispatch look like? Well, it's just a big dispatch. It's got a sequence of tests and branches. And remember what that does. The very first expression, for example, uses a primitive procedure called self-evaluating. Again, we're just burying some abstractions here. It uses that procedure, that operator, to look at the expression held in the EXP register and decide if in fact it's true. If this expression is self-evaluating, it's going to set a bit on the condition register, which means the next instruction, the branch instruction, will jump to that label, to that point. If it's not true, the condition bit does not get set, and the sequencer immediately goes on to the next place, looking at the next test. And of course, we'll have a whole sequence of these tests, dispatching on the type of the expression off to some piece of the register machine to do the work. This, of course, looks just exactly like the big cond we saw in earlier evals, dispatching on type. At the end of all of this, we'll have a failsafe, a go-to that jumps to some piece of the code that handles the fact that we've given it an expression it does not know how to deal with. Although we haven't shown it here, and it's certainly in the textbook, we also know the order in which we need to test for the different kinds of expressions. We're going to first look at the primitives, and then we'll move on to the special forms, then we'll check for an application, and after that we'll go to the failsafe. But that order is important in terms of how we decide where to dispatch. Okay, now let's look at some of these eval helpers. Notice first of all that they use the same contract as eval dispatch, and that means that we can easily see how to build these. In particular, we know that the EXP and ENV register hold the expression in the environment. We also know that continue holds the return point, and we know what we want as output. We want the value is put into val, and then we want to head to the continue register, making sure the stack stays the way it was. Also notice that when we dispatched to here from eval, we didn't use the stack. We didn't have to save away something that says come back to eval when you've got the answer, because we're assuming that each one of these helpers is going to directly return the value to the continue register. There's that nice notion of saving the stack space. Okay, let's look at a few of these to see how we can do it, and we'll start with the easiest ones. For example, suppose the expression is just a number, a self-evaluating thing. Well, we know what to do. We simply take what's in the EXP register, that pointer to that element itself. We move a copy of it into val. We now have the expression's value in val. And what does the rest of the contract say to do? It says go to wherever continue points to. Return to the place that asked for this value, and we've satisfied the contract. Stack is in the same state, answers in val, and the registers may or may not have been written, but we don't care. If the expression is a variable, a symbol, well, we'll just manipulate the environment. We'll use that primitive procedure to get the thing out of the environment, again, putting the value in val, or rather, if you like, a pointer to whatever the value is in val, since it may itself be tree structure. Again, we can go straight to the continue point because we don't have to do any use of the stack. In fact, we're saving the use of the stack, and we've satisfied the contract. If we get a first special form, a lambda, we need to do a little more work. In particular, if we're evaluating a lambda expression, notice we're evaluating, not applying. If we're evaluating a lambda expression, we just want to create a procedure. But that procedure needs to wrap several things together. So we'll use our selectors, our built-in selectors, our primitive selectors, to get out the pieces. First thing we'll do is get out the parameters of the lambda from that thing that's pointed to from the EXP register. We'll temporarily stick that in unev because we need a place to hold on to it. We can then go off and get the body of the lambda and stick that in EXP. Notice the order. Having held on to the parameters, we're safe now in clobbering what was in the exp register because we're no longer going to need it. We've replaced the exp register with just the body of the procedure. Finally, we can actually create the procedure. What's that say to do? Use the primitive constructor, the thing we're assuming is there syntactically, gluing together the parameters as a list or tree structure, the body also as a list or tree structure, and of course the environment, since we want to attach that as well, and whatever is returned by make procedure, which we know is just some other tree structure or list structure sitting in the heap, we put a pointer to that thing in a val. Why? Because our contract says we want the result in val, and having done that, we can go straight to continue. Again, notice, no manipulation of the stack, no wasted space, and we're straight to where we want to be. So here's just a recap of that in words. As we said, self-evaluating just puts the expression itself as the return value in val. A variable uses the abstract operation to get the thing out from the environment. And for a lambda, we know what we want to do. We want to make a procedure out of this, so we simply glue the pieces together, temporarily using EXP and unev to store things, and doing it in the right order so we don't lose information along the way. So what have we done? We've basically just translated the pieces for simple evaluation, or rather evaluation of simple expressions, into register machine manipulation. Eval dispatches off based on the test of the type, and each one of these simple pieces simply constructs up a new return value and goes to the point with that value in the right spot. Now let's look at a more complicated evaluation. Suppose the expression we're trying to evaluate is a definition, a define. We know generally what we want to do. We need to get out the variable part of the definition, the name, and we need to get the value of the expression that is the value part of the definition, and then we need to bind them together in the environment. Now, let's look at how we would do this. Well, the first part is easy. To get the variable out, we just use that abstract operation on that tree structure to go into the tree pointed to by exp and pull out the piece that corresponds to the actual definition of the variable, or rather the name that we're going to use to assign a value to. And notice again, because of that abstract type there, we don't know whether that's in the second place or somewhere else. It will do the right thing with the tree structure. Temporarily, let's stuff that in unev, because we're going to have to hold on to that while we go off and do other things. So there's the easy part. What else do we need? Oh, we need the value of the other expression, the value that's going to be bound to this name. But that means we need to evaluate it. And aha, that says we've got to both get that part of the definition into the EXP register. That's the first line in blue. We take what's currently in EXP, pull some pieces off of that, and stick that back into EXP. Notice we're assuming we can do this safely, and in fact we can, because we're no longer going to need the expression that was in EXP. We've done that because we've saved away the other part we needed, the variable name, up in unev, so we're safe in doing this. The next thing we need to do, though, is we need to get that expression's value. And that says we've got to go to eval dispatch. We've got to do this cycle one more time. And we know what the contract says for eval dispatch. For eval dispatch, we need an expression in EXP, we need an environment in ENV. Ah, that's okay, we've left the same environment there. I mean, that's exactly right. We want the value of this expression with respect to the overall environment in which we're doing the define. It's a choice of our language. What else do we need? We need a pointer in the continue register as to where to go when I get that value. And then, we need to worry about the stack. So notice what we've done. We've put a new expression in X, the first blue line. We've put a new label in continue. That says where to go back to when I want to come back with the value. And we're about to head off to eval dispatch. Notice what would happen. If we went to there now, eval dispatch would get the value of that expression, whatever it is, and by contract, when it came back to ev definition 1, the next spot in this code, the value of that expression will be sitting in val, exactly where we want it. Also notice the form, setting up some input registers, putting a label into continue, going to a place, and coming back to the next point immediately below where we've got the value we want. But notice a problem. If we just did that, we can't guarantee that the expression we're evaluating won't overwrite some of the other things that we have in our registers. In particular, we're going to need the variable name in unev. And we don't know that that application isn't itself something that's going to create a new environment. Therefore, we have to do the following. So before we set up the contract, that is, before we set up the registers that are input registers to eval dispatch, we need to save away the state of the world. We save unev because we know we're going to need it. We save env because we don't know that somebody else won't use a new environment as part of the process. And we save continue because, again, we're about to clobber it. We're about to change it to come back to here, and we need to keep track of who called this particular evaluation. And having done that, then we can safely go off with the dispatch. Now, notice, once we've gone to eval dispatch, by contract, when we come back to ev definition 1, we know that the resulting value is in val. The stack is back to the state it was just before we went there. And therefore, we can restore the state of the stack. That is, move things back off the stack into the registers we wanted. And again, notice they're done in the opposite order in which they were saved because it's a last in, first out kind of structure. And having gotten here, we can then actually do the definition. That is, go off and take the name, the value, and the environment and create a new binding of that name and that value in that environment. Having done all of that, we then make a choice. We need to put some return value in val. And here we could have anything. We choose to put in just the constant OK. We could have chosen to put in the value that we actually created. We could have put anything else in. It's our choice in terms of what is returned, since basically a define is around for the side effect, not for the actual value being returned. And then, having done all of that, we can go off to register continue to whoever asked for this when we started. So let's step back from this and recap some of the bigger issues. First, why did we save away unev, env, and continue? Well, we answered it. Basically, we know that they're going to need those values after the recursive call, and we don't know that they aren't going to be overwritten by eval dispatch. They may not be. We may have wasted some space here, but we can't guarantee it. And the contract for eval dispatch says they could be written. Since I need the values when I come back, I better save them away. Second, why did we use exp in the recursive call? Well, again, we're relying on the contract from eval dispatch. It expects the expression to be evaluated in exp. So we need to move that part of the definition, that expression part, into exp so that we can guarantee when we come back the right answer is in val. That's what eval dispatch is expecting. Now we also know that eval dispatch expects env to be set up. It should have an environment in there. But we didn't do an explicit assignment here. And as we said, that's because the expression part of the define is evaluated in the same environment as the define itself. Hadn't been changed, we don't need to change it, it's just sitting there. And finally, why did I use unev in line 1 in that first line? And the answer is it's just temporary storage. I could have used any other register. I could have decided to create a special register just to hold these things, but that's kind of wasteful. I need to, however, move that piece of the expression, the variable name, into some place so that I can take the rest of the expression and put it into exp. I do need temporary storage. The choice of which register is really up to me. Notice that for the expressions dealt with to this point, we didn't really need to worry about the stack much. The only place was in the definition part, and even there it was a simple use of the stack. More particularly, whenever we dispatched off to one of these expressions, we could rely on whatever point in the continue register that asked for that value to simply be the same point we could return from, saving any stack use and simply going directly to the point when we've got the right expression done. Now we can move on to the heart of the evaluator, which is dealing with recursive calls and trying to optimize them to be tail recursive whenever possible. Let's start by looking at ifs. Again, we know what we should see. We know that from our normal metacircular evaluator. We need to use a selector to get out the predicate. We then need to evaluate that expression, and depending on the value returned, whether true or false, we need to either evaluate the consequent or the alternative. So let's see what we have to do to make this happen. Well, we know the exp register holds a tree structure that has a big if expression in it. So in principle, we should just go in and pull out the predicate part of that if expression, using something that walks the tree and gets that piece, and stick that into exp. That's the second line in blue. That's allowing us to basically put the predicate expression in exp. We could put a label and continue that says, come back to here when you're done, and then we could head off to eval dispatch. In fact, that's exactly what we want, because eval dispatch will evaluate that expression with respect to, the same environment we're in now, because we haven't changed that, And when we're done, we'll come back to ev-if-decide, the label we put in, with the value of the predicate sitting in val. That would allow us to then carry on with the rest of the process. As with the last case, however, we have to be careful. We know the contract for eval dispatch says expression in X, environment in env, return point and continue, all of which we've done. But we have to worry about the stack. In particular, remember, we started off with exp holding the whole if expression. When we come back with the value of the predicate, we still need to be able to get a handle on either the consequent or the alternative to do the right thing. So we better save away that pointer that's in the exp expression, or exp register rather, so we'll still have it. Similarly, we can't guarantee that the environment won't be changed as part of that recursive evaluation, so we better save that away. And of course, whoever asked for the value of this if expression still wants that answer returned. That was initially sitting in continue, so we need to save that away. Said slightly differently, we have to obey the contract for eval dispatch, which says any register that holds a value I might need upon return, I better save away because I can't guarantee it won't get clobbered. Having saved those away, we can now do the dispatch in blue. When we come back, we can just restore the stack back to where we wanted it to be. And at the end of that third of the last set of red expressions, or red instructions rather, we know where we are. We have the value of the predicate sitting in val, the stack's back to its normal state, and we can now carry on. And what does carry on mean? Well, it says we can now execute a branch. We can make a decision about which thing to do. We take what's in val, which we know is the value of the predicate, and we check to see if it's true. We set a condition bit if it is. If, in fact, that condition bit is on, then at the next instruction, the program counter will cause us to jump to ev-if consequent, down to that point in the code. If, on the other hand, the value is not true, the condition bit will not be set, and the sequencer will then drop down to the next instruction, which we've labeled as f-if alternative, just to put a value or a label there so we can see it, which means we're going to go straight to evaluating the alternative. In either case, we do basically the same thing. We walk the tree, pulling out the part of the expression that is held in the exp register, and putting it back into exp. In one case, we get the consequent part out. In the other case, we get the alternative part out. But we're simply putting a new expression in exp. Notice what else we have. The environment's back to the environment we started with. And the continue register holds the pointer to the place that asked for this. That is, the place we were at when we tried to get an if expression evaluated. So in both cases, we can now go straight to eval dispatch. And there's that nice tail recursion. Because what does this say? It says, whatever answer you get out for evaluating either the alternative or the consequent, whichever branch I'm down, that answer is exactly the answer I want for the entire expression. There's no sense coming back to this part of the code just to pass it along, just to restore the continue register, if you like, so I can go straight to the place I want. No wasted space on the stack. And there you have an if. We save away some state, set up a call to eval to get the predicate, come back, restore the state, and then check to see which branch we want to take. So let's just summarize these key points. Notice that for the predicate part of if, we do a normal recursive call to eval. That is, we save some state on the stack and return, including a return pointer, do the work and come back to that point. On the other hand, for both the consequent and the alternative, we use that tail call optimization. There are no saves and restores. We don't have to save something, do the evaluation, and come back and restore it just to return. We go straight to the place we want it to. And indeed, this is exactly what makes the loop in sfact iterative. The fact that that if says the value of whatever that if expression is in fact exactly the value I want back, allows me to have this happen. To drive this point home, here's the code we would use without the tail recursive call. It says, basically, having done the evaluation of the predicate, we come back to the if alternative, and here's what we need to do. We save away the continue register. That's the person who asked for the value of the whole if itself. We put a new label into the continue register, put the alternative into exp, just where we want it to, go off to eval dispatch as before. When we come back, we have the answer in val. We then restore continue, just so we can go to that point. There's that useless use of the stack, that extra piece of information that we'd have to use up on the stack. Of course, we do the same thing with the consequent version of this as well. By not wasting space on the stack, by using this tail call optimization, we create a structure in which iterative things behave as iterative things with no extra use of the stack. And now we can see very nicely the difference between a normal recursive call and a tail recursive call. Having seen one example of a place where tail recursion helps, let's now move on. Second place where it's going to help is with sequences, things that begin with begin, for example. As before, this is a helper for eval. It has the same contract as eval dispatch. It expects an expression in exp. It expects an environment in env. It expects a continue point in continue. And it's going to come back to there with an answer in val. Here, however, we're going to do things slightly differently for a reason that will be clear shortly. In particular, when we get to this point as a dispatch, something that's a sequence with a begin, we're going to save the continue register on the stack, move all of the other parts of the expression, that is, all of the clauses themselves other than the label begin, into unev, and then we're going to go off to a special thing called fsequence. Fsequence also has a contract. It's something that's going to be used by begins and by applies, lambda bodies that also have a sequence of expressions inside of them. And here's the contract for fsequence. It's going to expect a list of expressions, tree structure as before, in this case sitting in unev, the set of things that have not yet been evaluated. It's going to have an environment in env, just as before. And on the stack, it's going to assume that the top value is the return point. So in other words, we're not going to keep the return point and continue. We're going to leave it at the top of the stack. And we'll see why shortly. Given those inputs, it's going to do all of its work and return a value in val as its output. That'll typically be the value of the last expression in the sequence. It's going to write everything, because it's going to call a val without doing any saving. When it's done, though, we want the stack to be restored to the state it was. That is, with the top value removed or popped. And that means it will put it back to the state it was before we hit ev begin. So here we go. We now take the sequence of things sitting in unev, and we take the first one and move it into exp. What are we doing? We're setting up to do an evaluation. We want to evaluate each of these expressions in turn, so we're setting up for the contract for eval. We've moved an expression into exp. We still have an environment in env. And in general, we could just go straight to the process we want to do. So let's skip the next two lines. What do we have to do? We need to save away anything we might need, which includes everything in unev, because those are the things we haven't yet evaluated, and the environment, because we're going to need it when we come back. We put a new label in continue, and we go off to eval dispatch. That's very nice. It says when we come back to fsequence continue, we've got the value of the first expression in val, and we'll have everything else as before, so we can restore the state of the stack, putting in the environment back in env and the things we haven't done yet in unev. We can then go on to all the remaining expressions, in other words, remove the first one because we no longer need it, and go back up to fsequence. So we basically create a little loop in which we take each expression in turn, set up for the dispatch to eval, do the work, restore the state, and carry on. So that gives us a little loop that basically walks down the expressions in order, evaluating them. What happens when we get to the last expression? Suppose, in fact, we now have the last expression loaded up into exp as part of that first instruction. We do the test to see, is this the last one? And if it is, that branch is going to cause the program counter to change, and we'll jump down to fsequence last expression. Why? Well, here we can handle things the way we did with if. We can be tail recursive. And in particular, we can now restore continue. Remember, we saved that way back up at the beginning of ev begin. It had been sitting on that stack. And no matter how we used the stack in evaluating each of the expressions in the sequence, we always got back to the same state with that thing sitting at the top of the stack. What do? We put that thing back into continue. That was the pointer to the person who asked for this begin to be evaluated in the first place. And having done that, we can now go to eval dispatch. So this again is tail recursive. We've put the last expression in exp. We've restored a pointer into continue. And now we've cleared the stack. We're not going to waste any time getting the value of the last expression, coming back here, and then having to again restore continue in order to go back to the person who asked for it. We go straight to that point. And now we see that sequences similarly take advantage of tail recursion on the last expression to avoid unnecessary use of the stack. So in fact, to recap, we've seen that tail call optimization on the last expression. That, again, we need so that loops, like s factorial are iterative, not just the if, but the loop itself, the recursive call, will always be, in fact, an iterative thing. Or said another way, since sfact has two expressions in its body, we can evaluate the first one, the display, then evaluate the second one, but make sure that we don't have to save anything on the stack for each one of those recursive calls. That makes the whole thing iterative. What else do we have? Well, we know that the evaluation of each expression puts the result in val, but notice in the code we never seem to use val. Well, that's okay, because we know that those things are done basically for the side effect. They don't have to be returned to anybody. Only the tail call to eval will put the final result in val itself. That happens automatically, and as a consequence, that is the value returned for the value of this entire sequence of expressions. Everything else is just ignored. We do it for the side effect, mutation or define. So why bother to have that return point sitting on the top of the stack? And the answer is it's essentially just an optimization hack. We avoid having to save and restore every time around the loop. We certainly could have done that. We could have been more clean about always doing that save and a restore each time we went around the loop so that we always have the stack in the same state when we enter the loop. But it's kind of a nuisance. As a pure performance optimization, we can save that by simply doing the restore on the last expression. We can't do the same thing, of course, with unev and environment because they're used inside the loop. And therefore, we actually do have to do the saving and restoring as we walk around the loop there. Nonetheless, we now see again how we can build an expression into our register machine for evaluation, in this case something that deals with sequences, and we can see how we can play this trick to make it very efficient. Okay, what about the heart of eval? Eval really comes down to doing an application. That is, taking an expression that's an application and reducing that to an evaluation of a new expression, the body of that procedure, that application, with respect to a new environment. So what happens when our evaluator hits something that's an actual application? Let's sketch out the stages, both talking about what parts of the register machine code we're going to need and what they correspond to in terms of a normal eval. So when we hit an application, we're going to dispatch off to a helper for eval that actually says, here's an application, do the right pieces with it. That will first get the value of the operator. In terms of the normal evaluator, we'd know we'd get the operator part of the expression and do an eval on that. We'll have a corresponding piece of the register machine code that gets the value of the application operator. We're going to have to hang on to that, obviously, while we set it up. And in fact, we know we should be sticking that into proc in order to set up for the apply. We also need to get the values of the operands, the arguments. In terms of normal evaluation, we just map a little evaluator down each one of those expressions, walking through them and creating a new list, a list of the argument values. We'll have a corresponding part of the register machine that is a loop that walks through each of the pieces of the expression register, getting the values of the arguments. And then, having gotten a value for an operator and a set of argument values, we can go ahead and do the actual application. And we'll send that off to another dispatch that decides whether this is a primitive or compound procedure in order to decide how to apply that procedure to that set of arguments. Now, let's look at all of those pieces in turn. Let's actually start with the bottom one first. Apply dispatch. This is the thing that's going to do the actual work of making the procedure be applied to a set of arguments. And like eval, an eval sequence, it also has a contract. Its contract says, I expect the proc register to hold the actual procedure, a pointer to the structure that actually corresponds to that procedure. I expect argle to be a list of the actual argument values, and I expect the stack to have a particular state. I want the top value on the stack to be the return point. That's going to be similar to what we saw with F sequence. Our applied dispatch will then do the work, and when it's done applying that procedure to a set of arguments, it expects the value to be returned to be sitting in val, that's its output. It will write everything, because it's going to call ev sequence inside of it, so it's going to, in fact, overwrite everything we need. We're going to have to be careful about that with the stack. And when it's done, when it comes back to the point that asks for all of this, it expects the stack to be restored. That is, the top value removed, that top value that we know was the return point that we started with. We're going to come back to that in a second, but with that contract, applied dispatch is actually quite straightforward. Since proc holds the actual procedure, we can do a dispatch. We test to see if it's a primitive or if it's a compound thing. That is something we've built ourselves with Lambda just by looking at the labels. Again, it's an abstraction about how we manipulate the structures. And depending on either of those two cases, we dispatch off to something that does the actual work, which we'll get to in a second. Otherwise, we head off to an error handler that says we have an unknown procedure type here. If it's a primitive procedure, one of the built-in pieces of hardware, then we just do the work. We have some abstract operator called apply primitive procedure that connects to the hardware that takes the procedure in proc, the list of arguments in argle, does the work, and puts the answer into val, exactly where we expect it. We're then going to restore the continue register. Remember, we assumed that that was sitting on the top of the stack, so to satisfy the contract, we put it back in, and we then go to that point, now having completed our work. Suppose it's a compound procedure. That is, it's something that was built with a lambda. Then we know what to do from our normal evaluator. We need to first get out the parameters of the procedure. That's part of that list structure that represents the procedure. And we'll stick those in unev temporarily. We need to get the environment part of the procedure. We'll stick that in env, again, temporarily. Notice we're just walking the tree structure of what's represented in proc to get those pieces out. Then we take the list of parameters, currently sitting in unev. We take the corresponding list of arguments, now sitting in argle, because that's where we expected them to be. We take the current environment sitting in env, and we build a new environment. Again, this is just some manipulation of tree structures we saw before, but what gets created is a pointer to a new environment, and we store that in env. Notice what we have. We now have a new environment in ev, an extended environment that inherits the original environment but has a new frame, the frame that was dropped by the application of the procedure. We then take what's sitting in proc, that procedure, walk through it using tree structure to get out the body of the procedure, which we assume, by the way, for our evaluator is a sequence or a begin, and we put that in unev. That's nice because that's exactly what we expected, and now we have satisfied the contract for ev sequence. Notice what's in place here. We've got a continue point on the continue register, on the top of the stack rather, still, that's where we put it to be. We have an environment in ev, we have a list or sequence of expressions in unev. We can go to ev sequence. Having satisfied its contract, when it gets done, it will also restore the state of the stack, doing that pop of the continue register, and go to that place with the value of the last expression sitting in val. Exactly what we want. So now we see compound application does what we'd expect. Builds a new environment and evaluates an expression or sequence of expressions with respect to that new environment. So let's quickly recap. First of all, why have that return point on the top of the stack? Well, we're going to assume, or we have assumed, that the body of a procedure is a sequence of expressions. And we know ev sequence is assuming that is part of its contract as well. We're going to put it on the top of the stack for exactly the same reason. It's a performance optimization. We also know it has to be saved on the stack in order to go off and get the value of the operator. We need to have it there anyway. So we might as well just leave it there as long as possible in order to avoid unnecessary operations. And then to recap for a compound application. Notice that we use ev sequence rather than eval dispatch because we're going to allow bodies of procedures to be sequences. Notice again the use of the tail call optimization, which was going to be allowing us to have tail recursion in our system. Also notice that both env and unev are used as part of the call because they're required by the ev sequence contract. That's why we set them up in that particular way, rather than using exp, for example. And as before, notice how we use env and unev in the first two lines just as local temporary storage places. As before, we could have used any register. These are just simply holding on to things while we get the other pieces we need. Now we can go ahead and actually do the work to set up for that application. So when we dispatch off to an application, the first thing we do is save the continue register on the top of the stack. As we saw, that's going to stay there until we actually finish everything up and restore it as we do part of the actual application. Having done that, we need to then get the value of the operator. And this now looks a lot like what we did before. We're going to put the operands temporarily into unev so that we can take the expression register and put the operator expression into exp. Having done that, in general, we want to go off and do an eval on this. So we'll put a label into continue and go to eval dispatch. As before, though, we again save env and unev because we're going to need them when we come back. So this has exactly the structure we'd expect. And when we come back from eval dispatch to the point labeled ev apply did operator, we know that the value of the procedure was sitting in val. We can restore the state of the world and move that over into proc. Before we do that, though, let's look at something. Again, why bother to save the environment away? And here's a nice way of seeing it. How do we know that the expression that's sitting in the operator is just a name? If we knew it was just a name, we wouldn't have to save the environment because we wouldn't change it. We could just go look it up. But of course, that expression could itself be another procedure application. And if it is, we see that we're going to create a new environment. We just did that with the application. Therefore, we have to save the environment away. Otherwise, this has the same form we saw before. We're setting up the contract for val dispatch, saving away whatever parts of the world we're going to need, and when we come back, restoring and moving on. In this case, putting the value into proc, getting set for the contract for apply. And again, to recap, notice how we put continue register on the top of the stack, but leave it there untouched until either we hit primitive apply, where we saw we do the restore, or until the end of ev sequence in the body of a compound apply, that is in the body of the expression, does the restore. So the restore could happen in one of two places, but in either case, when we're done with the application, the stack is returned to the state it was. In terms of getting the value of the operator, we do a standard call to eval dispatch, just saving away the set of expressions that are the operands because we're going to need them, and saving the environment because we're going to need that to evaluate those operand expressions when we come back. At the end, as we noted, we put the operator in proc because we're going to use that, if there are no arguments, immediately, directly, as having it in the right place. So having gotten the value of the operator and put it into proc where we want it to be, we're now set to run through this loop. And the loop should basically get the values of all the operands and accumulate them together into argle so we can head off to applied dispatch. Let's look at what we do, though, in a little more detail. First, we initialize argle to be an empty list. We've got to get it set up at some starting point. And then we check to see if, in fact, there are any arguments to this procedure. If unev, the set of things we haven't done yet, is empty, there are no operands there, then we're set. We have a procedure in proc, we have an empty list in argle, we can go straight to apply dispatch and complete the actual application. If there are arguments, however, we're going to have to run through this loop of getting their values. So in this case, and only in this case, we actually save proc away. Notice how we've saved some work on the stack if we don't need it. We'll come back and restore proc later on, but we put the procedure away, and now we run through a loop. When we know the general form of the loop, we're going to take each expression in turn, each thing in unev, put it into exp, and go off to eval dispatch to get the answer. And then when we come back, accumulate that into argle. In fact, where that purple line is, there's a bunch of stuff on the next slide that we'll come to. We'll skip that for now. We know that we're going to simply continue to accumulate values in argle until we get to the point where we're going to get the value of the last operand. In that case, we can go down to ev apply last arg. And what does that do? It puts a new label in continue and goes straight to eval dispatch. Oh, there's that tail recursion again of saving us the extra work. We know that when we go off to eval dispatch, we don't have to come back here and restore unev or anything else because we don't need anything more here. So when we go off, we get the value of the last argument and come back. At that stage, we restore argle, put this new value into argle, and restore proc. What have we done? We now have a procedure in proc, we have a list of arguments in argle, and at this stage, we're set to go off to apply dispatch. Remember, the continue point is still sitting on the top of the stack. And in terms of evaluating each operand, that chunk that was missing from the purple spot there, well, it has the form we'd expect. We save away state we're going to need, the environment and the things we haven't evaluated yet, put a new label and continue, go to eval dispatch. When we come back, we've got the value of that expression, we restore the state, add it to argle, change what's in unev to remove that first expression because we've done it, and go back around the loop. So we simply loop through this sequence of getting a new expression into exp, going off to eval dispatch, when we come back, taking its value and accumulating it in argle, just using the stack to save away things we're going to need when we come back. So here are the key things to note about this chunk. And I know we're throwing a lot of code at you, but you should be able to step back and see these points. First of all, in this loop, getting the values of the operands, as we pointed out, we check to see if there are no operands, so that we avoid going off and doing the evaluation of something if we just got an empty list. Now, why did we save proc way back at the beginning and restore it at the very end? Why not just have it hang around? Well, we know inside the loop we're going to call eval. And its contract says it writes proc, or it may write proc. In fact, one of the operand expressions might be an application, in which case we're going to need proc there. So we need to save it away in order to make things available for use for other kinds of sub-expressions. Same reasoning applies for argle. We've got to save it away and restore it because we don't know that one of the sub-expressions might be, in fact, an application that will need to reuse it as well. So that contract for eval is helping us decide what things we have to save away. On the other hand, we said we need both proc and argle, but why save argle inside the loop and proc outside of it? Aren't we doing a lot more work? And the answer is we are, but of course we need it, because we need to change argle every time around the loop. We need to get it back, add something to it, and save a new state away. Whereas proc isn't going to change. It's the same procedure no matter which expressions we're evaluating in terms of arguments. And finally, why do we have that save argle before the branch to ev apple last argument, before we go off to do the last arg? Logically, it really goes with the saves and eval of one operand. Why not put it there? And the answer is basically it's a hack. This is an optimization that saves one instruction, and it's not really a big deal. It would have been more sense to logically put it in with those other things that were part of the same set of saves. But there you have it. So in fact, there's most of the register machine code for an evaluator. We've really taken the idea of eval and reduced it down to register machine operations. Now, we've cheated a little bit. We've gotten all these abstract operations to manipulate expressions and environments. But we know those are just tree manipulations, and in fact, we could easily build each of those pieces. Indeed, if you look in the textbook, you'll see very detailed specifications for how to do those in register machines. The other thing we see is how we can reuse the same machinery, using the stack to save away state while we use that contract between eval and apply to get values of sub-expressions. And finally, we've seen how we can be clever. We can avoid using the stack when we don't need it. We can use that idea of tail recursion to say, if the value of this expression is the same value as the value of an overall expression, simply send it straight back, rather than keeping track of things on the stack that I don't need. Otherwise, now we've got eval. We've built a register machine version that connects basic hardware to a universal machine, to an evaluator that lets us put in any expression. To help you see how this little explicit control evaluator in fact incorporates the ideas of eval and apply, we're going to run through a very simple little trial simulation, a simulation of computing factorial of 3 for the standard definition of factorial. In fact, I don't really care about the version of it. You may find it convenient to go back and print out slides that correspond to all the pieces of the register machine code so that you can actually follow along as we do this. If you want to do that, stop, do it, and come back and redo this part of the lecture. To run through this simulation, here's what we're going to do. We're going to mark every time we hit one of the labels, every time we hit a new piece of the register machine code, if you like. So under label, we'll specify where we are. We'll indicate what's in each of the registers: expression, environment, value, procedure, argument list, unevaluated, and continue. And we'll show what's on the stack. And we're going to use the stack growing out from left to right so that the top of the stack is at the right as we move along. We'll also highlight in red the things that have changed from stage to stage so you can see how we move things through this register machine. Okay, to start things up, we have an expression loaded into the exp register, an environment loaded into env, and something on the continuation. And basically some infrastructure takes care of this. It reads in the expression, in this case calling fact on 3, loads it up into x, has a pointer to the global environment in env, and puts a pointer to the read eval print loop, or REP, in the continue. And we go off to eval dispatch. Eval dispatch, of course, checks the types of these things, figures out it's an application, and does the following. It saves away the continue register on the stack and puts a new marker into continue that says, come back to did the operator when we're set, saves the environment, and saves everything else but the first part of the expression. Those are things we still have to get. It also, by the way, puts those in unev, as we see along the way, and then loads up a new expression into exp. So the things we're interested in here is it puts the first part, the operator expression, into exp, and is going to get its value with respect to the same environment, having on the stack the things it still has to do. Eval then looks up the value of fact. It goes off to eval dispatch, figures out it's a name, looks it up, and puts that value, that procedure in val, and heads to did op. And at this stage, we got the value of that first expression saved away. Having done that, we then move that value into the proc register, getting ready for apply, restore off of the stack the things we haven't done yet, and set up to go through the loop. In fact, we're also going to save proc on that proc register because we realize that we don't have 0 arguments here. We have things to actually do. So notice where we are. We're getting set to run through the loop of getting the values out of unev and accumulating them into argle, into that empty list, so that we will end up with a procedure in proc and a list of values in argle ready to go. So we move the first expression out of unev, move it over into exp, which is where we want it to be, because we're going to go off and get its value. But we also notice that this is in fact the last argument, so we're going to handle it separately. Notice we've also saved away argle on the list, because we're going to have to restore it in order to accumulate things. And now we can head off to eval. Notice we've unwound things. We're now getting the values of the expressions. We're going to get the value of 3 with respect to the global environment and expect to accumulate that into argle. So in fact, we do that value and go to the next spot, which, since this is a self-evaluating thing, simply puts that value in val. Notice what we have now. We've got the value of the only argument, the last argument, in val. We got a procedure so we can in fact accumulate those things and head to apply. Or in other words, we restore the state of the world. We accumulate into argle the list of arguments, in this case just the list of the single value 3. We restore the procedure back into proc. And when we get to apply, notice what we have. A procedure in proc, a list of arguments in argle, and a place to continue at the top of the stack. Exactly what we want. The fact that the rest of the registers hold things don't matter to us. They're just residual things left over. Since this is a compound procedure, apply basically creates a new environment, E1, by taking the list of arguments in argle, the list of parameters in the thing sitting in proc, and binding them together, creating a new frame. It then puts the body, the sequence of expressions, in unev, which is where we expect it, and heads off to sequence, or val sequence. Notice what we have. We have a sequence of things to do in unev, an environment with respect to which we are going to do that evaluation in env, and still sitting on the top of the stack is the place to go back to, the continue. And now we simply run through the loop. We pull each expression out in turn from the unev things and check to see if it's the last one. In this case, there's only one expression there. It's just a big if. So we put that into exp. We've got an environment with respect to which we're going to do the evaluation. And since it's the last thing, we can actually get set to restore the state of the world. And in particular, we move to restoring the continue register off the stack. And now we're set. Notice what we have. We have a valuation of an expression, a big if in this case, with respect to a new environment and a place to go to when I'm done. And indeed, we've actually gone through a very nice cycle. The cycle is that we've gone from evaluating an expression with respect to an environment into the application of a procedure with respect to a set of arguments, which has reduced to evaluation of a new expression with respect to a new environment. And notice by the time we get from that cycle of the first eval to the second eval, the continue registers back to where we started from. In between, we've simply got through a little loop where we get the values of the arguments out of unev and accumulate them in argle, saving away on the stack anything we might need in the meantime. But the overall loop is simply shown there in those nice boxes. So now let's pick up the pace. Again, we started off evaluating factorial of 3 with respect to the global environment. After a series of steps, we saw we got down to evaluating an if expression with respect to some new environment, E1, which has some bindings for variables in it. And we want to get back to the same place on the continuation when we're done. What happens inside of the if? Well, basically, we know what happens. We grab the first part, because if is handled specially. We get out the predicate, move that into exp, the exp register, saving away things we're going to need on the stack, and putting a new continuation point into the continue register, and we head off to eval, get the value of the predicate. After some number of steps, we know by contract when we get back to that place, we have the value of that predicate sitting in val. In this case, it's false. So having done that, we can now say, restore back into the register the expression we saved away, restore back, in fact, the same environment because we've gone that back, and restore back also the read eval print loop into continue. That is, put the state of the world back and move into exp the consequent, the part of the thing we want to deal with because, in fact, the expression test was false. Notice what we've got. Evaluation of a new expression, one of the pieces of the if, with respect to an environment and a place to go to and continue. Okay, we know from factorial that expression is times n factorial of n minus 1. And now we see the other piece that's going to happen here. We're going to get the value of this expression with respect to E1. That means we first get out the value, or we want to first rather get the value of the operator. We move that into exp, saving away things in the stack we're going to need. Once we've gotten that value in val, the value of star is mul, we can restore things and run through the loop in which we actually go ahead and get the values of the arguments. Eventually, after skipping some steps, we're going to come to the following state. We're going to be evaluating the recursive call to factorial, factorial of n minus 1, with respect to the same environment, E1. We've got the procedure in proc, the thing that's going to do the multiplication when we're done. And in argle, we've got the value of the first argument, n, which has the value 3. Sitting in unev are the remaining things that we have to do. We have to get the value of that expression. And notice what's sitting on the stack. We've got the place we eventually want to return to at the bottom of the stack. We've got the procedure saved away, and we've got the argument list saved away. There, by the way, are our deferred operations, because what's going to happen now when we take that value sitting in unev and go and do the work? Well, let's look. Notice again, by the way, how evaluation is run through a loop. Getting evaluation of factorial of 3 with respect to one environment has reduced to evaluation of a body with respect to another environment, which has reduced to evaluation of a recursive call with respect to another environment, but with some deferred operations on the stack. And there's the second piece of the cycle. There's where, in fact, we need the stack usage, because this is a recursive process, not an iterative one. And what happens when we carry on? Well, basically, we're going to run through the same kind of cycle. To get the value of factorial of n minus 1 with respect to some environment, we're going to walk through the same cycle of dealing with this as an application, reducing it to, in fact, evaluation of a body, which will eventually unwrap to the state shown at the bottom. We're going to have to get evaluation of factorial of n minus 1 with respect to a new environment with a different value of n. And on the stack will be now 2 saved operations. We'll have the stack frame, if you want to think of it that way, at the bottom of the stack for the deferred operation for the top level multiplication. You can see the procedure and the argument we're going to need. And on top of that, at the top of the stack, is another one that says we also need to do a multiplication by 2 of whatever we get out of this. Key point is to see how the stack is now growing, gathering together information for each of the deferred operations as we unwrap this recursive call into more and more evaluations of the body or the recursive call to the procedure with respect to a different environment. And indeed, we can now see this top level unwrapping. Evaluating factorial of 3 with respect to the global environment reduces to evaluating factorial of what we know will be 2 with respect to a new environment with some deferred operations on the stack, which unwinds one more time. In this case, it has to be recursive. We have to keep track of those deferred operations, and we see how the evaluator automatically puts them on the stack for us. Eventually, when we get down to the primitive application, we'll be able to start unwinding all of these deferred operations, reducing the stack back down. But the order of growth of the recursive procedure is now nicely shown by the growth of the stack. Shown in red are each of those stack frames corresponding to each deferred operation. And we also now see how the difference between a tail recursive call on an iterative procedure will allow us to avoid that stack usage, but a recursive procedure that's inherently recursive will have to use the stack. Overall, though, we've now built our register machine version of an evaluator.